Okay. So let's get started with motion planning lecture number 8. Today our topic will be Open Motion Planning Library, a small introduction, also with some coding examples. And yeah, just to recap, last week we had optimal kinodynamic motion planning, a special focus also on planning with and without steering. So yeah, I think Wolfgang talked a lot about the difference between them, that if you have a steering function, then planning becomes easier, but having the steering function is very difficult to compute. And on the other side, if you have just a propagation function, then it's a bit more difficult to plan, but on the other side, it's pretty easy to define a propagation function. And then you also had a look at the space cost approach, which is another planner which is asymptotically optimal, AORT, which plans in cost space and which basically combines this feasible kinodynamic planning with asymptotically optimal kinodynamic planning. Okay, yeah, and today, as I already said, we will have an introduction to the Open Motion Planning Library, which I would say is one of the biggest libraries in motion planning, well maintained. And we will look a little bit at the general structure of OMPL, and then afterwards we will look at how you can actually set up problems in OMPL, geometric problems, kinodynamic problems, and if we still have time, then also we will have a look at how you can set up benchmarks in OMPL. Okay, OMPL, just a general overview. It's an open source software. It's basically a collection of almost all sampling-based motion planners out there, mostly written and maintained by researchers in motion planning, and very modular, easily extendable, and it is also used by several robotics companies. And here is one screenshot from a paper called Motion Benchmarker. It was basically built on top of OMPL, and you can see here some benchmarks of a lot of different robots in different environments. And so this is all basically possible by building upon OMPL, by using the benchmark capabilities of OMPL. Here is another example from OMPL, from this paper here by Kingston. It basically shows this NASA Robonaut 2 moving along in a space station. And here the problem is also that we have some contact constraints, so the robot should also make contact with the environment at certain points here. And with OMPL, we can still plan such environments by using a constraint framework inside of OMPL. So yeah, as you can see, it's very versatile. You can do a lot of it, and it basically can solve almost all of your motion planning problems which you can define. Small history of OMPL. It was originally created by Lydia Kavraki. This is a person up here. She's a professor at Rice University in Houston. The main maintainer of this library is Mark Moll. He was previous director of research at Picnic Robotics, which is also one of the robotics companies which rely heavily on OMPL. And there are a lot of contributions by many researchers worldwide. So usually if someone develops a new motion planning algorithm, very often they also contribute to this OMPL library and extend it. Currently version 1.6 was released in 2023, and the first version was released in 2014. So roughly already almost 10 years since version 1.0. And the capabilities of OMPL are that you can solve geometrical motion planning problems as we defined here in this lecture. You can also solve optimal with arbitrary objectives. You can, of course, solve also kinodynamic problems with a steering function or without a steering function by just defining a propagation. And you can also benchmark planners. So there's a very nice library there where you can just plug in a lot of different planning algorithms, and you can just compare them. How do they perform on a certain environment? Okay, So let me give you a small overview about the class structure in OMPL. So if you want to set up a motion planning problem, you need at least two structures. One is called space information and the other one is called problem definition. So space information basically contains everything which is a bit more permanent, like the state space, and problem definition contains everything which is not so permanent, for example, the start and goal configuration or a cost function. And so the input to the space information is a state space, a state sampler, and a state validity checker. So those are all functions on the state space. And for the problem definition, what you have to define are start state, goal, and optimization objective. And if you have defined those two classes, you can plug them into planner. And you can use any planner you want, RT, RT star, bit star, PRM, PRM star. And by just defining those structures here, you can just do planning, get the solution path back, and visualize it. And yeah, small question for you. What do you think are the necessary structures? So what are the classes which you definitely have to initialize to solve a planning problem? And what are the ones which are more optional, which you don't have to define? Yeah, exactly. So state sampler and optimization objective have a default value. So for the state sampler, it's uniform sampling. And for optimization objective, it's just the cost in the configuration space. The state validity checker, it has also a default. It will just return true. Of course, if you have obstacles, then you have to define something there, but it's also not required to do planning. Okay, so now I want to go a little bit into details, what all those classes which you have to initialize contain. So I will start here with the state space. So in the state space, we have different spaces which we already looked at. For example, the real vector state space, which we use, for example, for manipulator arm. We have also SE2 and SE3 implemented, which we use for mobile base or for a drone. There are also some more, I would say, exotic state spaces like Dubin state space, which is a car with constant forward velocity, or a time state space, where you can basically just go forward in time. And so this is, of course, useful if you have to plan around dynamic obstacles, if your environment changes over time. And the primitives which all of those spaces implement are one, a distance metric, which tells you what is the distance between two configurations in your state space. We also have a uniform sampling function, because I think, in lecture 2 or so, we already talked about that sampling is not so easy if you're not in RN. So you have to do a little bit more smarter things in SE2 and SE3. And the same, of course, is true, for example, in 2-bit state space. And finally, we also have an interpolation function, which tells you how you go from one point to another point in your state space, which is, of course, also different between state spaces, especially if you have rotations. And the only requirements for those state spaces are that you have to define some bounds. You have to tell it where, for example, the real vector state space begins and ends, and you have to also tell it what is the dimensionality of the state space. But otherwise, this is actually very versatile. You can basically define almost any robot with it, and it's very rarely that you have to actually define a new state space, for example. Then we have also state validity checker. So this one is the one I would say is a bit more difficult, because the state validity checker has been implemented in such a way that you can just plug in any collision checking engine you want. And so you have to basically write a little bit of an interface to it. As I said, it basically interfaces with any collision checking library. For example, you can plug in this flexible collision library, which we talked about earlier in the lecture. There's also a nice one, which is called Proximity Queries Package, PQP. And the state validity checker basically defines two functions. One is valid, which basically just tells you if all the constraints are fulfilled. And then we have a function clearance, which returns you the distance to the nearest invalid state. And of course, this is a bit optional because computing clearances in an environment is usually very computationally hard. And so usually planners are not relying on clearance computations. Okay, something which is also a bit interesting is the state sampler, where you have a lot of different choices to make. So the state sampler basically just returns you states from a given state space. We make a difference between unbiased samplers and biased samplers. So the default is basically an unbiased sampler in your state space. This means it will just give you a very uniform covering of your state space. It will not bias any points into certain regions of the state space. And so this is basically the default option which you have, basically just uniform sampling of your space. However, in OMPL, there are also some biased samplers implemented. I will talk a little bit about 3 of them. So one is obstacle sampling, where you try to put more samples near obstacles. Then we have clearance sampling, where you try to do the opposite. And then we have also deterministic samplers, which basically just return you a deterministic sequence of samples from your state space. Okay, let's just have a quick look at all 3 of them. Obstacle-based sampling in OMPL. It's basically the idea that instead of sampling uniformly everywhere in your state space, you try to sample close to your obstacle or to the constraints of your environment. So instead of having samples everywhere, you try to have them on top of the surface of your obstacle or near the boundary of your state space. And small question for you, what do you think are advantages of biasing samples towards obstacles? Yes.
I think most optimal paths, when talking about distance, are like going very sharply around obstacles. Like the path would be going through the obstacle. So sampling near the obstacle would make sense if we want to already at that point find a really good path instead of like sampling through the empty space.
Yeah, that is true. I think you were next.
Also, for the narrow passage problem, it's a big help.
Yeah, so those are basically the 2 main advantages, narrow passages and path length bias. So of course, if you are in a narrow passage, then obstacles are very close, so it makes sense to sample near obstacles. And of course, you have this, I would say implicit path length bias that usually optimal paths have this property that they come very close to an obstacle, if optimal is for you the shortest path length, of course. Okay, and here's a small example. So for example, if you have this environment where you have a small narrow passage in the middle, then with obstacle sampling, you usually get quite a bias towards samples which are near here. And so this basically can accelerate planning. And in OMPL, there are 3 different types of obstacle sampling. There are different types because it's not so obvious how you would actually sample near an obstacle. And so that is why we have actually different ideas of how you can do this efficiently. The first one, it's just called obstacle-based sampling. It's basically the idea that you sample a point. It has to be a valid one. Then you sample another point, which has to be an invalid one. And then you move from your valid sample towards your invalid sample, and you stop at the point where you actually make contact with an obstacle. And that is basically your point, which you will return in sampling. And of course, this will have the property that it's very close to an obstacle. So this is one idea. Another idea is that you have what is called a Gaussian sampler, where you also sample around until you find a valid sample. And once you found one, you sample another sample in a Gaussian neighborhood. So for example, this one. And if those are actually both equivalent, so for example, both are valid, then you just discard them. However, if you sample and you find one is valid and one is invalid, then you keep the valid one. And the main reasoning behind this is that, of course, if you have a valid sample and you have an invalid sample in a very close neighborhood, then this valid sample must be pretty close to an obstacle. And so this will also give you a bias towards obstacles. And yeah, something which I haven't touched upon is that if you just sample on obstacles, you don't actually get samples very close to, for example, a narrow passage. And usually you want to have also a little bit of a bias towards those narrow passages instead of like sampling around everywhere. And so to do that, we have something which is called the bridge state sampler. And the idea here is that you sample 2 points. And you do that so that you can find points which are very close to a narrow passage. And so this is done by just sampling around until you find 2 infeasible points. And then you just take the midpoint of them. So for example, here we have found 2 infeasible points. We take the midpoint. And then we just check if the midpoint is valid or not valid. And if it's not valid, then we just discard everything. And we sample again 2 invalid points until we come to a situation where you have 2 invalid points. You sample the midpoint, and suddenly the midpoint is actually feasible. And in this case, you can A, be sure that it's near to an obstacle, and B, you can be sure that it's actually inside of one of those narrow passages, because you know left and right of it, there will be an infeasible point, and in the middle there will be a feasible one. And so this gives you a good indication that this one here is actually a point inside of this narrow passage. So this is actually a very nice way of implicitly defining narrow passages and actually sampling and biasing points towards those narrow passages. And so this bridge sampler can give you a big advantage if you are in a narrow passage and you want to have more points in there so you can more efficiently plan paths. Okay, and so if you just continue doing that, then usually you get a little bit of a bias towards those points here. And so, if you're lucky, you get actually a big speed up in planning. Okay, and here is a small picture where we compared obstacle sampling and bridge-based sampling. So the idea is that here around there are obstacles in gray, and there's a small point robot here which should go from this side to this side, from green to red. And all those green squares here, they are samples which were drawn from the state space. And small question for you, which one do you think is actually the bridge state sampler? Yes.
The one to the right?
Yeah, exactly. And you can basically see this by seeing that most of the samples are in the narrow passages or here in the corners of the state space. And on the left here, this is the classical obstacle-based sampler where we have just a lot of points all around here on the obstacles. Okay, and question for you, do you think there are also disadvantages of using obstacle-based sampling? Any idea? Yes.
I mean, if you, for example, only have like very small obstacles, then you might like sample forever until you find the obstacles with your sampling.
Mm-hmm.
So maybe in this case it's not optimal, especially like for bridge sampling. I think it's maybe you don't find any bridges because the obstacles are shaped in a certain way or something like.
Mm-hmm. Yeah, definitely correct.
Also, realistically speaking, sampling, we will always drive very close to the obstacles, which might not always be what we want.
Yeah, exactly. Yeah, so I would say those are definitely both the reasons why obstacle-based sampling has some disadvantages. One, that sometimes you don't want to actually optimize path length. You might try to optimize something else. And then, of course, you have this trade-off between quality and runtime. So, for example, if your obstacle is very small or so, and you're trying to do bridge sampling, but there are, for example, no narrow passages, then, of course, you sample a lot without actually getting any benefit. So yeah, it definitely depends on what kind of environment you have. So sometimes you definitely get an advantage, but it really depends on your environment. Okay, and because sometimes you don't want to optimize over path length, but instead you want to, for example, stay a little bit far away from obstacles. There are also other state samplers implemented, for example, clearance-based sampling. So clearance-based sampling has basically, I would say, the opposite idea of obstacle-based sampling. So instead of going very close to the border, you try to stay away from the border as far as possible. And you want to find actually samples which are, yeah, as far as possible away from the boundary of your state space and also from the boundary or the surface of your obstacles. What do you think are advantages of doing clearance-based sampling? Yes.
The resulting path is likely to have a high clearance of obstacles, so it's a very safe path.
Yeah, exactly. So here you would have like a bias towards maximizing your clearance, and of course sometimes this is actually the thing that you want. You want to stay away from obstacles because it would be very costly to collide. And so this would be basically, yeah, a safety mechanism, clearance as a safety fence, basically. And it also reduces, by that, the uncertainty in execution. So if you execute your path with your robot, you are less likely to collide with obstacles, even if there's some uncertainty in execution. And in OMPL, there are two different types of clearance-based sampling implemented. One is called minimum clearance, the other one is called maximum clearance. And so the idea with minimum clearance is basically that you just take a certain distance from your obstacle and you define a zone which is not allowed to be touched. So it's basically a minimum clearance zone around your obstacle. And so if you sample and you find a sample inside of the obstacle, then this is of course invalid. But if you also sample something inside of this zone around the obstacle, then this is also invalid. And so only points which are actually outside of the obstacle and outside of the zone, they are deemed to be valid. And in this way, you basically just get a lot of points which are definitely outside of your obstacle. And the other idea is this maximum or maximized clearance, where you sample a valid state, and then you take this idea of sampling in the Gaussian neighborhood of the state. You basically sample a lot of different points. Here in this example, we have 5 new points around this valid sample, and you compute what is actually the clearance of all those points. And so if you look at them, then maybe this point down here has the highest clearance of them, and it maximizes locally the clearance. And you would basically return this one here as your next state. And by that, you can basically just have this implicit bias towards states which have actually a maximum clearance or which maximize locally the clearance. So those are the two big ideas. And of course, there might be some disadvantages. Does anyone have an idea? Yes.
I mean, like, it doesn't give you any guarantee how close you are to an obstacle. So you might actually end up with samples very near an obstacle.
What do you mean?
I mean, like, if I sample maybe inside a narrow passage,
Mm-hmm.
and maybe I want to avoid that, and
Yeah, but it's of course always this trade-off between being too close, but also trying to solve it. So yeah, if you have a narrow passage and you have to actually go through it, then there's no other way than just returning samples there. And I would say that this is actually a good thing that we still return samples even in those narrow passages. Yeah.
I think like calculating clearance for samples explicitly might be expensive depending on how you implement it. And I think like especially for minimum clearance it might be easier to just like add padding to the collision meshes.
Mm-hmm.
Since you guys basically have the same effect and don't have to explicitly calculate clearance.
Yeah, so this is, I would say, the biggest disadvantage that we have to actually compute clearance. And yeah, as you also said, narrow passages, we still get samples there, but I would say even if we have samples in narrow passages, there is this implicit bias that we try to go away from narrow passages. So one other disadvantage would be also that yeah, you get less samples in narrow passages. And even if you hit the narrow passage, then if you sample around and find something which has higher clearance, you try to actually steer there. And of course, this would be a bias towards clearance cost, and maybe this is actually not what you want. You don't want to stay away from obstacles. Maybe you are in a scenario where you have to actually touch an obstacle or be very close to an obstacle, and in that case, it would not make sense to use clearance sampling. So there's a clear influence of sampling and optimization objectives. So if you have an optimization objective, then sometimes it makes sense to switch your sampler to a different sampling function, and so those two are actually a bit need to be in sync. Okay, and then finally in OMPL we have also deterministic sampling. So I think we already touched upon that in one of the earlier lectures, which is basically just the idea that instead of just randomly sampling, you just have a sequence, a predefined sequence of points, and you just use a predefined sequence of points to sample. And do you think this also has some advantages?
I mean, you have some sort of guarantee that you have a more uniform distribution across the space. So like what sometimes happens if you sample randomly is that you don't get any points at in some area, and then like it just doesn't really discover the space. So if you like do it deterministically, I think that could help with that.
Yeah, exactly. So yeah, we already touched upon this dispersion idea last time, I think. So what is also an advantage is that it's more predictable. You know basically where you sample, so you don't have cases where you have like a clustering of points in some areas of your configuration space. And because you can control it, you can also better distribute it, and you have this low discrepancy or low dispersion, which we talked about last time, where you basically minimize the area in your configuration space, which is free of samples. And I think one of the main sample algorithms we talked about is this Halton sampling, where the idea was basically just that you just subdivide your space multiple times, and you basically, in this case, get a finer and finer and denser sampling. And I think last lecture I also showed you this picture here, where you get on the left uniform sampling, where you get a lot of like clustering of points here at different positions, and where you have also like larger areas of the configuration space which are free, which is especially bad when you go actually to higher dimensions. And on the right you have this more denser or low discrepancy, low dispersion Halton sampling, where you have actually minimized the amount of free space between samples. Okay, any idea of what might be disadvantages of deterministic sampling? Yes.
If we have a very specially placed narrow passage, we will never sample there, and never or in a very long time solving the problem.
Mm-hmm. Yeah, I would definitely say this is a disadvantage. So with random sampling, you could also have the case that you have like a bad sampling sequence and you don't sample in a narrow passage. But at least you have like this more randomized sequence where you have maybe a bit better chance to sample there. Yeah, and of course, it's also, again, a trade-off between efficiency and runtime, because usually, especially if you use a Halton sequence, it takes a little bit of time to compute the sequence. And usually it's easier to just uniformly sample points instead of like computing what is the next step in my sequence. And this might have like a little bit of overhead in computing the sequence. And then, of course, this will take longer to plan. Yeah.
Is there ways to do like biased deterministic sampling?
I don't know actually of any. I guess if you already know what kind of environment you have, you could bias it. There are also approaches where you learn the biasing of your sampling function. Basically, you learn a sampling function by looking at like 1,000 environments and then learning where you should actually sample if you have a new environment. And this definitely makes sense if you have like a very similar bunch of environments in which you plan. For example, if you drive around a city or so, then maybe crossroads look kind of similar, so you would maybe learn something there. But of course, if you want to be very general, if you want to solve everything, then biasing would basically not work against uniform sampling on all kinds of environments. But yeah, definitely makes sense to bias there and maybe also use some deterministic biasing from a learned function, for example. Okay, any other questions about sampling? Okay, and then in OMPL you can also define goals. And so there are actually a lot of options which you have. You can, of course, just define a goal state, which is just a state plus, for example, an epsilon neighborhood. You can also define multiple goal states. This might be, for example, valuable if you grasp an object where you have different positions of how you want to grasp it, and you don't really care how you grasp the object, you just want to grasp it. You can also define goal regions, for example, a subspace of your state space. An example would be a manipulator arm on a mobile base. For example, you just want to have this mobile base inside of a certain room, but you don't care where exactly in this room you want to place the robot. And so that would be basically just a goal region. And each of those goals has also a primitive defined, which is called is satisfied. And this primitive just checks if your state is actually satisfied, if this state is actually in your goal. And it's basically very easy to define new goals by just implementing this is satisfied. Okay, another thing which we have in OMPL is this optimization objective. I already talked about that, you have different samplers for different things, and they are very closely related to the optimization objective. So what is implemented as optimization objectives in OMPL are, for example, path length, which just returns to the shortest path. We have also maximized minimum clearance, which is just the idea that you want to, over the whole path, maximize the minimum clearance, which basically is just the distance between the robot and the environment. And of course, you might have things like minimize arrival time. You want to reach your goal, but not on your shortest path, but maybe on the shortest time path. And the only primitives which you have to implement here is the motion cost. It's basically just the cost to go from X to Y. And as we already talked about, usually planners don't take this into account. You definitely need an optimal planner like RT star or PRM star, but then they take actually your motion cost, your optimization objective into account and can return you a more optimal path. Okay, any questions for that? Okay, then I would show you a small demo of how you can set up problems in OMPL. Okay, so yeah, what I want to do right now is to show you how you can set up a very small point robot problem, a geometric problem, and how you can solve it with one of the sampling-based planners in OMPL. And for that, I will just write here a small script. Just a second. So the first thing which we do is that we import some of the basic libraries from OMPL. So for a geometric problem, we need the space library and geometric library. And then we have basically 4 steps which we have to implement. So the first step is that we implement a state space. So let's say we just want to plan for a small 2D point robot, and in this case, we just define a real vector state space and for 2 dimensions. And we can also print this space with settings. And here I will just quickly execute this. So I'm using here the Docker implementation of OMPL. I just downloaded the image and I just run it here. And you can see here the output is basically my state space, which I have defined. And there is a minimum and maximum bound on the state space. And of course, this doesn't make sense for planning. And so that I also need to define some bounds. And so this is also pretty easy by just defining some real vector bounds of dimension 2. And with bounds, you can set lower and upper limits. So for example, here I just set the lower limits to -1 and the upper limits to +1. And if I execute this again, I will see that I still have the same bounds here. Of course, I need to set them to my space. And now if you execute it, we see that the space now has -1 and +1 as bounds. And so we can do some planning with that one. This is basically the first step which we have to do. And the second step is that we define a problem definition. Basically, we have to define a start and goal state. And so we do that by just calling base.state from space. We do that also for the goal. And let's say we want to start at -1. And we want to go to, let's say, +1. And so now we can define this problem definition, which we do like that. And what is missing? We still don't have implemented the space information. So, and we have to also set the start and goal state here to the problem definition. So let's see if this compiles. Okay, so this compiles now. We have defined a start position and a goal position for our problem. We have a space defined for our problem. And so the last thing which we have to do is to actually also define a planner and solve the problem. And so here I will just use a geometric planner, and I will just use the RT. And for the planner, you have to also set the problem definition. And then you can simply solve it by just calling the solve function. And the solve function takes as input a time. So you can just say here, I want to plan for 0.5 seconds. And if we execute this, we get some output, but it doesn't show us if it found a path here. So that is something which we have to get from the problem definition. So there's a function called getSolutionPath. And we can print this path. And voila. So this is basically a path which has now been planned by RT in this 2D environment. And of course, this is not super interesting because we don't have any obstacles. So what I want to do here is to also print this path and add some obstacles. So let me first visualize it. So, and to visualize it, I will use the matplot library. And so the matplot library has just this show command, which takes in x and y of the path. And so the only thing which we still need to do is to access x and y coordinates of the path. And so in Python, there is this function called map, where you can just iterate over all the entries in your path. So there's this lambda function here, where you can iterate over an object, for example, over this path. And this lambda function basically executes an operation on each of the states in the path. And here we want to just get the state 0, which is our x coordinate. And we will create a list of that. And we will also do the same for y. And so this should plot us the path. Let's see if this works. No, it does actually not work, because we need to get here also the states from the path first. OK, so it doesn't show us anything. And the reason is because it is run on Docker, and there's no connection to my monitor. And I couldn't figure actually out how to connect this Docker to my monitor. So if any one of you has an idea, please let me know. But in the meantime, we can also just plot it to a picture. So let me just do that. And then we can just display the picture. And voila. So this is basically a path in 2D for our point robot planned with RT. And what you can see is, of course, that this path has a very zigzag motion, which is very typical of all the sampling-based planners. And now I also want to add a little obstacle here, so that we can also see how the state validity checker works. And for that, I will just add a rectangle in the middle of the configuration space. And luckily, there are some primitives implemented in the matplotlib library. So I will just take this rectangle here. And I will use this rectangle to define a validity checker function. So first, let me plot this rectangle. So the rectangle has as input the lower left corner. So I will just put it at 0.5. And it has also a width and length. So let's say this is 1.0 for both. And with matplotlib, you can just add patches. And I will just add this rectangle as a patch. Let's see if this works. Of course, I have to do it like that. And voila. Now we have also a rectangle. And you can see that RT doesn't yet know how to actually do collision checking with this rectangle. It's because we didn't yet define a state validity checker function. So let me just do that. It's actually very simple to do that by just defining a function which is called isValid. And isValid takes as input a state, and we need to get the x-coordinate of the state and the y-coordinate of the state. And then we also have to check what are the coordinates of the rectangle. So the lower left corner of the rectangle is just the x value. And the upper coordinates of the rectangle are the lower ones plus the width and length, the width and height of the rectangle. Okay, so this gives you all the information which you need to check if it's valid. And what you can do now is just to check if your x-coordinate is larger than the lower bound and smaller than the upper bound. And if it's also true for your y-coordinate, and if it's true for both of them, then the state is actually not valid, and you can return false, and otherwise you can just return true. Okay, and now we have to tell the planner that this isValid function actually exists. And you do that by augmenting the space information class, and you can just call it here setState validity checker, and you have to define here a state validity checker function. And it takes as input just this function is valid. So now, if everything is correct, then the planner should know about this isValid function, and it should be able to actually also plan with it. So let's see. Yeah, so it worked. The planner knows now that there's a rectangle here and that it has to actually plan around the rectangle. And if we run it again, then it finds another zigzag path which is not touching the rectangle here anymore. Okay, and now you might say, okay, I don't like this path. It's so zigzag, it's not optimal. And so I want to have my planner also returning me something which is more optimal. And this is also super easy to do with OMPL. You can just set a cost function in the problem definition. And this is basically done by set optimization objective. And so there are, as I said, different optimization objectives implemented. So for example, one is this path length optimization objective. I don't know if it's actually called that way. Yeah, let's see if this works. No, there's no path length optimization objective. I forgot the I. Okay, so I still get this path in return because RT actually is not optimal. It doesn't know how to actually use this optimization objective. And so what we can do is that we use a different planner, for example, RT star. And just by changing here from RT to RT star, we now have an optimal planner. And this optimal planner will just plan for the whole time here. So let's set it to 1.0 seconds, and it will just not return you one path, but it also will try to optimize the path over time. And so it will take a little bit longer, but bless you. But in the end, you get actually back a path which is optimal. And if you run it again, then again, RT star will optimize your path, and it will return you this optimal solution here to go from the lower left corner to the upper right corner. And yeah, as you can see, you touch here almost on the outer end of this rectangle here. Of course, this looks a little bit like it would go through the obstacle, but this could be just visualization error, or you have the step size of your edge is not fine enough, which is used for collision checking. Yeah, but as you can see, it's actually very easy to set up those problems with OMPL. It's pretty versatile, and there are also a lot of different algorithms which you can plug in here. For example, you can also use a split star, which we talked about, and you can run it, and it will also give you an optimal solution or an almost optimal solution here. And of course, the longer you let it run, the more optimal your solution will become. And you can, in this way, compare different planners to each other. You could, for example, also write your own planner and have a look at how it performs against the other ones. Okay, any questions about this? Yes.
I suppose we will probably need this in a later programming exercise. So
Yeah, that could happen.
will you give us access to the code snippet?
Yes, so I will give you all the code snippets which I show you here. Any other questions? Okay, in that case, let me continue to our next topic, hemodynamic planning, and how you can set it up in OMPL. And for that, I want to just quickly go back to our initial slide here about the class structure in OMPL. If you want to do kinodynamic planning, you need some additional structures. And in this case here, you need at least a control space and a state propagator function, or a steering function if you have one. But at least you need a state propagator and a control space. And those two classes need to be implemented, and they need to be set in the space information class here. And so for the control space, I think in OMPL there are only two control spaces implemented. One is this real vector control space, which is basically just Rn plus some bounds, nothing new. But then you also have a discrete control space, which is basically a space which has a predefined set of controls. And one example would be motion primitives. For example, you are at a certain state and you have, I don't know, 20 motion primitives which you can execute. And this discrete control space basically would give you a way of how you can implement this. And this control space has basically just one primitive, namely this uniform sampling. It can tell you what would be the next control you want to apply. And it has some requirements. You need to set some bounds. You need to set the dimensionality. And in the case of the discrete control space, you also need to set the set of controls which you want to plan with. Okay, and then the more important thing which you have to implement is the state propagator. So the state propagator basically tells you if you are in a certain state and you have a certain control, how will your system evolve over time. So you need to basically define a dynamic system here. And it is defined, this propagator function, as a function propagate, which takes as input x, c, and t. So x is the state, c is the control, and t is time. And so the idea is that you start at x and you propagate the system forward with control c for duration t. And as output, you get a new state. And if you have it available, you can also implement a steer function, which takes as input x and y, which are two states. And this function computes you a control c and a duration t to move from state x to y. And this is strictly optional, so because sometimes you have very complicated dynamical systems where it is extremely difficult to compute a steer function, or sometimes it's even impossible to compute a steer function. But if you can actually do it, it is usually a good idea to do it because it can definitely speed up planning. I think, in one of the last lectures, we looked at that it's actually pretty difficult to plan with just propagate, but it's actually pretty easy to define just propagate. And from a user perspective, it's easier to just define the propagate function for a dynamical system. Okay, and I want to look at a small example of that, which is a kinematic car. So the kinematic car is just a car which can move around on the plane. It has a state space SE2, and this SE2 state space, yeah, is just x, y, and theta, which is just position and orientation of the car. You have a control space U, which has two parameters. One is forward and backward speed, and the other one is the steering angle. And so this is basically those two parameters, U1 and U2. And then what you have to do to plan with the system is to define the dynamics. And the dynamics is just a function of the state and the control. And in the case of the kinematic car, you can use some geometric arguments to come up with this dynamical systems equation, which is shown here in the lower right corner. And it is basically a function of the angle of your car, which is theta here, the position of your car, xy. It is also a function of the length between the back axis and the forward axis. And it takes also into account the steering angle of the car, in which direction are you currently putting your steering wheel. And this function here down here, you can basically just infer it from geometric arguments from this figure here. And this basically tells you if those positions are all set and you have U1 and U2 as your parameters to move around, then the system will basically move in a certain way according to this dynamics equation for a certain time t. And so this gives you all the information to basically plan for this kinematic car. And that is exactly what we will do right now. So I will just show you another small demo here. So let's get back to the one which we had here. I will just create another one, which I call demo 2. And so this time we don't only import base, but this time we also include control and geometric. So we need all three packages here from OMPL to move around with our robot. And so our first step here is again that we set up the state space. So let me just add some comments here again so that it's a bit more structured. So our space here in this case is an SE2 state space. So SE2 doesn't need any parameters, but we have to again define some bounds. We can just take the same bounds as we had here from our last space. So we want to set them between -1 and +1. And let me just see if this compiles. Yeah, so this works. And then we don't only need the state space, but we also need a control space. And for our kinematic car robot, we will just define a control space as this real vector control. And with 2 dimensions. And here again, we need some bounds. And the control space bounds, they should be a bit different to the space bounds, in that we want to set both of the parameters individually. So for example, for the first parameter, which is the speed of the robot, we want to set low and high values to -1 and 1. And for the steering angle, which is the first parameter, we want to set it to 0.5. And then we can just set the bounds for the control space to the control bounds. And what I still forgot is that the control space needs as input also, I think, the space. OK, so this worked. And next, we need to go do the same thing as we did before, namely defining the problem definition. So I will just copy a little bit here from our old example. So again, we have a start and goal state. And in this case here, we also need to define the orientation. So I will just set it to 0. I need to do the same here with the goal. And what I forgot is to set also, create also a space information class. So this can be done here with control space information. And this takes as input the space and the control space. And it takes, it has basically all the structures which we need for planning. And now we can define the planning problem. And this time we need a control planner. And so there are different control planners implemented. So the basic one is RT again. And we also need to set the problem definition. And then we can, again, solve this kinodynamic problem. And let's see if this works. And it tells you that it doesn't work because the state propagator is not yet defined. And so what you need to do here for the kinodynamic case is, of course, that you define the forward propagation, the state propagator function. And so how you do that is basically by just implementing it. It takes as input a state, a control, a duration, and it returns a target. And so first, let me just get all the data here from state and control. So x and y from our state, and we will also get the angle of our state. And so we want to also get the control of u1 and u2 here. And so this is basically everything we need. And now we can just implement this kinodynamic function here, which we defined. So I will just use L equal to 1 so that it's a bit easier to do. But you can, of course, use any L to define any kind of kinematic car which you want to define. And so you get here new states. One is, what did we have here? U1 times cosine of x of CR. And I don't think that cosine is implemented here in Python, so we need to also use NumPy for it. And you can do the same for y. Okay, and then finally we also need to compute the new yaw state, and so this is just the tangent of u2 times u1. Is it correct? Yeah, seems good. Okay, and now finally you can just set the target states here. And you do that by computing x plus duration times xn. And you do the same here for y. And the same for the orientation. Okay, so that should be everything you need for the propagation function. Now you have to actually tell space information, the space information class, that this propagation function exists. I think it's this one. So let me just run it. And yeah, it seemed to have worked. We still don't have any output, so I will also do the output as we did it for the geometric case. So I can just copy here all the structures which we had. So first we get the solution path, we get the states from the solution path, we print the path. Let's see if that worked. I didn't save it. Okay, and so now it actually printed me out the solution path, and the solution path is actually given by how you can apply the control and for how many iterations you apply the control. So it's a bit more complicated, but we can also just visualize it again in the same way as we did for the geometric case. So we get x and y, we plot x and y, and we save it to an output figure. And let's take the second one. Okay, and of course I need to define matplotlib here. And okay, so there was one more error, namely that if we get back the states here, we have now an SE2 state space, and you can just index it, but instead you need to actually use this get x and get y method to actually get x and y coordinates, and voila, so this is the output of our kinematic car, which goes here from -1 to +1. You can see here that there are some weird back and forth motions. So this is basically something which we would expect if we use just RT, the kinodynamic RT version. Something which I want to change now is that I want to only go forward and not backward. So it means that we start from 0, 0, and we just go to +1. And I'm also using a different planner, namely SST, which will hopefully give me a bit more optimal paths. And so let's see if this improves things. Okay, yeah, so that is pretty optimal path for the kinematic car using SST. And yeah, so this looks pretty good actually. And of course, we can also do now the same things which we did before. We can add here a small isValid function. So we basically add a small rectangle here again. In the middle, we have this isValid function. We need to change here how to get x and get y. And we have to also set this validity checker. And now let's see if this actually works. Rectangle is not defined. Of course, I have to include it. And I also have to visualize it, of course. Sorry for that. Okay, and now it should actually show me, an obstacle, and it should show me an optimal path to go from left to right. And you can see here that the upper coordinate is 0.75, so SST has not yet converged to an exact solution, but it only returned you an approximate solution. And I want to just move the obstacle a little bit so that we can also see if SST can actually plan around it on the left side. So let me just move this a bit to the right. Okay, and you can see here already that SST was not able to reach the goal here because the problem got a bit more difficult. And so usually what you have to do is give it more time to actually solve it. So let's give it like 10 seconds or so. And usually that should be enough for a 2D planning problem to find good enough solution. No, it didn't. So yeah, so I think this was just a little bit too difficult.
Maybe the problem was that we can't go backwards, right?
Yeah, but it should basically be smart enough to just go forward around the obstacle. But yeah, so maybe the steering angle was actually not enough for that one. And I think also it should find something in. Okay, so at least it found a solution now. It's not yet super optimal, but you can see here, I think that was really the problem, that the steering angle was a bit too tight. But you can see here, not yet super optimal, but it goes already into the direction. And something which you can see here is, for example, that there are sharp corners, which is a bit weird because we have a dynamical system and the system can also only move forward in time. Why do you think there are sharp corners here? Yes?
Because of the visualization, because we just take the points and measure a multiple distance.
Yeah, exactly. So the real path here is actually one where you don't go here along straight line segments, but instead you have like this dynamical system equation. And if you really want to visualize it, you need to, like, for each state, look at what kind of control and duration you have, and then you just step forward in time to visualize it. And I'm just visualizing here the states at which we need to apply the next control, and that is why we have those sharp corners here. Okay, so that is how you set up a kinodynamic planning problem. Any questions about it? Okay, so the last thing which I wanted to show you is how you can also set up benchmarks. And for that, I want to just create a new script. So we can basically use our old kinodynamics problem, which we had here. And, maybe I will just take the geometric problem. Okay, let me take the geometric problem. Let's just remove the visualization here. And now I want to just compare different planars to each other. And for that one, there is a small benchmarking library implemented in OMPL. It's in this package called tools. And you can just write here benchmark, tools of benchmark. And so this benchmark class, it takes actually as input something which is called a simple setup, which is very similar to the space information, but it takes a little bit more, it has a little bit more information. So let me just and we don't need this problem definition anymore. And so I think this is basically everything you need to define a benchmark. And so for the benchmark, you can just add planners. So for example, let me just add bit star, and let me add RT, and let me add RT connect. And so now you have to also define what is the max time and how many times you want to repeat this experiment. So let's say max time is 1 second and your run count is 5. So you want to basically run each planner 5 times for a maximum amount of 1 second. And that is everything you need to run this benchmark. And then you can just call this function here benchmark.benchmark of this query. And it should return you some results. OK, let me just execute this. OK, so I didn't yet gets the right space information pointer, because the simple setup is basically now my space information structure, and I have to actually get space information from there. And now it works. So you can see here, it does this benchmarking, and it doesn't produce me any output. That is because I didn't yet tell it that it should actually save the results. So let me quickly do that. And let me also remove this bit star planner, and instead I will just add, for example, PRM. So let's see. Okay, so it should have actually created me a benchmark file here, and I can use this OMPL script to actually convert this benchmark to a database file. So you can see here we have now a benchmark.database, and there's online a function, not a function, a website, which is called Planner Arena. You can either run it like locally, like I do it here, or you can just go to, I think, plannerarena.org, and you can upload your benchmark file. And it will basically give you a lot of different tools of how you can visualize it. So what you can see here is the time it took for RT, PRM, and RT Connect. You can see here that RT and RT Connect find it immediately a solution, while PRM takes a little bit more time. You can also, for example, look at the solution length. You see here that PRM took a bit more time, but instead the solution cost was actually lower than RT Connect and the normal RT. And you can see here always the median of the solution length, and also the box here is basically just the uncertainty. I think it's a standard deviation around your median. Okay, and so of course you have a lot of different options here. You can see, okay, how many of the cases were solved, and so solved is here 100% for all the planners. And of course this was a very simple example, so all of them solved it. But of course if you have a bit more complicated problem, then you get more interesting results here. But this was just to show you how this works. So basically you have here, you can upload here your benchmark database, which you found from your Python script, and you can just have a look at all of the settings. Okay, any questions for benchmarking? Okay, cool. Then we have everything for today. So yeah, just to summarize, we had a small overview of OMPL, class structures, different options for sampling, for example. I showed you how to set up kinodynamic problems, and we looked at some coding examples. And I would say here are the 4 most important links for OMPL. Of course, one, the main website, which you can find here at kavrakilab.org. OMPL is also on GitHub. You can submit issues or requests there. And then something which I just showed you, this Planner Arena, which is a very nice way of how you can visualize any benchmarks which you found. You just need to convert your benchmarks to a database file. You can just upload it here on plannerarena.org. And you can look at it, download PDF versions of your solutions. And finally, we have also this web app. I didn't show you that one, but it's also pretty nice. You find it here at omplapp.kavrakilab. It's basically a front-end GUI for OMPL. There you can basically load a lot of different scenarios, and you can just plan there, and you have like a graphical interface. Most of the scenarios are like very classical motion planning scenarios, like, for example, moving a piano around in an office building, and you can also look at that. I think it's pretty nice to just see how different planners actually perform. Okay, any questions? Yes.
What do you use if you want to do 3D problems with meshes and stuff? Like what do you use to visualize that?
Well, yeah, so you can actually do that with this OMPL app. You can just upload, I think, their URDF file or something and some meshes. But yeah, if you just want to do it from the Python script, you basically just need a loader in your isValid function, and you can, for example, use FCL, which can load some meshes, and then you can just do collision checking in this isValid function, and that's all basically.
And for visualization?
Yeah, if you don't want to use Matplotlib, I think there are also other things like, I don't know, MeshLab, for example, I think has a visualization also from Python. Yeah. Okay, any other question? Okay, then that's everything for today. Thank you very much.